talking about like the 10% France, lately in Europe there's a lot of increase in the fees for credit card. Like, do you think that this magnitude is bigger than this lower?
Our estimates are exactly like the fees. I'll show you the estimates. They're exactly like the fees. So to me, even though I'm saying that, well, it seems to be that we're estimating the fee. So that's what I said. I'll just do like, just write like, I mean, bubble tobin was a fantastic model in the 50s. This is sort of like a, tiny incremental new version, but written the way you write stuff after the 70s. So you cannot write down stuff properly. So, okay, so there are two Poisson arrival rates here, I forgot to say. And that's just all incidental. There is one that with some probability, okay, this is the way your real cash balances in between adjustments are smooth. This is your consumption per unit of time. This is inflation, erodes them away. This is the cost that you pay. What you're doing is you're minimizing the cost. And these are your withdrawals. Tau are stopping times. Left and right stopping times because your cash is continuous. And there are two events for which you're taking these expectations. And the two events are either your cash gets stolen, which triggers a withdrawal. So think about your cash gets stolen, then you'll get more money. Just a way to bring this opportunity cost. It will look like an interest rate, essentially. And the other one is that you actually find a free withdrawal opportunity. So it's easier actually to Bellmanize this model and to write it this way. It turned out to be that you could combine the two P's into only one, because for the purpose of solving the problem, it's kind of the same. And then to have an opportunity cost that is equal to the real rate plus inflation plus P2. It's just the way it works out. So I'll briefly describe the mathematics that is used to solve it. It's kind of completely standard. And then I talked a little bit about the estimation and kind of what you get from this. Okay, so once you walk away from the bank, you should be with the amount of cash that you are happiest. So you're minimizing the opportunity cost. So call that level of happiness B star, or minimum cost. So that's just, B is a function that says, if you have this much cash, how happy you feel. And then you minimize it by your choice of Z, let's call M star, the amount that you walk out the bank. So not how much you withdraw, it's sort of like your target. So that minimizes the value function. In between periods, this is your Bellman equation. Your discounted rate R times B, that's a flow value, this is a continuous time. Then you pay the opportunity cost R times M, and then you have two changes of the value function per unit of time. This is a smooth change. The value function changes because M changes, that's B prime, and M changes because you consume or inflation erodes away. If you've never seen a value function in continuous time, there's just no way you will get it for this, but just think about your land release or something, it'll go over very soon. So then this is the probability that you find a free withdrawal which will trigger an adjustment. So you swap the current value of your value function by the one in which you optimize the cash holdings. So that's a standard looking. Notice something, M star, if you knew M star, this is an ODE that has an explicit solution. This will simplify a lot the computations and the estimation. The fact that the value function is essentially known in closed form. And so here I just giving you the boundary conditions. What are the boundary conditions? This is what happened in the range of inaction. And when your cash is equal to 0, remember like in the graph that I gave you, you're forced to withdraw. Meaning they're going to go to the optimal one plus paying the cost. There is another piece that is if you somehow end up with so much cash, you will deposit it. But this part is sort of irrelevant because you'll never get to that. Mathematically, you have to consider it to solve it. And then you could show that this function is convex, so the minimum actually is achieved at the point in which the derivative is 0. So really the boundary conditions are this one, and this ODE in the middle. It has an explicit solution. I guess a figure maybe in order. That's just an example of the value function. It's a cost function. So it's, convex as it should. And then this is the value of M star. So your life is like this. When you have M star, then inflation plus your consumption push the M this way in terms of time series. And eventually you have a free withdrawal opportunity, then you come back here. Or you come back here, but eventually sometimes you will hit 0, in which case you have to pay the cost B, and you see this difference between the two is B star plus B, where B star is effect. That's why this part is sort of irrelevant, but you can solve it. This doesn't have a return block. Nice. Oh, okay. So what are the results of this? Just what you think that it will happen. This is a smooth version of the model. This combines a simple, what I call the steady-state model, with the intuition of precautionary motive model. The return point is just a function of B over C times R. Now notice that in Baumol-Tobin, M over C also was a function of, remember I had this parameter B hat, that it had a B and a C and an R on the bottom. So that's something common to it. It's actually common to all inventory models. Second, it has another parameter P that will shift this function. This is the optimal return point. The optimal return point is one of the determinants of how much cash you have in average. It's not the only one because it will also depend on how fast you replenish. The elasticity of the optimal return point turned out to be between 0 and 1/2. Baumol-Tobin was 1/2. The other model has in a segment 0 and in a segment 1/2. This model has this randomness, so it's a smooth version of that. And in fact, the elasticity goes when P goes to infinity, the elasticity is 0. When P goes to 0, you have Baumol-Tobin, it goes to 1/2. So expand the whole range. Okay. And then this says that if you were to fix B and consider a very small p, the model behaves like Baumol-Tobin.